Welcome to MA 405 at Bellevue University. This course is Modern Geometry. Instead of having a weekly playlist for you to watch, in this class much of your learning is discovery-based. However, I do understand that it is much more helpful to be able to watch someone go through a proof than to try to come up with one completely on your own. So each week I will provide one video for you. That video will go through one or two proofs or talk about what it is that we're learning that week. This week we're going to go through two proofs. Just a quick reminder, your discussion board each week is to complete one of the proofs from your homework assignment. It goes without saying that the proofs that I go through with you should not be the proofs that you used in the discussion board post. Let's get started. This week we're going to go through two proofs, and the first of these is the Isosceles Triangle Theorem. And we are to use SAS, which is the side angle side theorem, to prove the following theorem, which is Euclid's proposition I5. The Isosceles Triangle Theorem says if triangle ABC is a triangle and AB is congruent to AC, so those are the sides of a triangle, then angle ABC is congruent to angle ACB. So let's get started. When we complete a proof, I'm going to be looking for certain things. I'm always going to be looking for a given. I'm going to be looking for a diagram. I'm going to be looking for a what to prove. And of course, I'm going to be looking for your proof. So those are the four main things that I'll be looking for in every proof that you complete. To get started, we're going to complete the given statement. Now, many students just use exactly what is written here, and sometimes that works and sometimes it doesn't. So when we write our given statement, we want to be specific. This one actually is specific and says if ABC is a triangle. So the given is going to be let triangle ABC be a triangle. And specifically a triangle where the side AB, or the segment AB, is congruent to the segment AC. And my diagram is going to be exactly that. I'm going to have a triangle A, B, C, and I have AB is congruent to AC. My what to prove. So what to prove is the second part of this statement. Then angle ABC is congruent to angle ACB. So again, we're trying to show that this angle and this angle are congruent. Now, before we get started in the proof, I want to point out a couple of things that are not made perfectly clear in your textbook. Here we're talking about congruence. When I'm talking about congruence, I'm saying that the segment AB, so notice I'm going to use the segment above it, is congruent to the segment AC. If I were talking about the measures, which of course is related to congruence, if I'm saying the measure of AB, I would say is equal to the measure of AC. Similarly with angles, if I'm saying the angle ABC is congruent to the angle ACB, I'm using angle and congruence. If I'm talking about the measure, I'm going to use M for measure, ABC, and then I would use is equal to the measure of ACB. So keep that in mind as you're working through your proofs, basically for the remainder of this course. But I digress. Let's get back to our proof. Our proof is asking us to show, and they've given us a hint to use SAS to show that those two angles are congruent. Now, many students try to create a second triangle or maybe some line that bisects. This one is actually a lot easier than most people make it out to be. All I'm going to say is since angle A is congruent to angle A, so now I've got angle A congruent to angle A, and I've got AB is congruent to AC, we can say triangle ABC is congruent to triangle ACB. So again, I've said I've got side BA, angle A, side AC is congruent to side CA, angle A, side AB. So it's the same triangle, which of course makes sense, but we're saying that those triangles are congruent, and the order in which I say those triangles are congruent is obviously quite important because it tells me which sides correspond to which sides. So it's not just that I decided to change the order. I'm saying, yes, in fact, AB is congruent to AB and is congruent to AC, BC is congruent to CB, and AC is congruent to AB. That's how those triangles are congruent. Why does that help me? Well, I have to say I'm saying the triangles are congruent by side, angle, side. Now, if I know two triangles are congruent, then I know all of their corresponding parts are congruent. Now, again, this is not something contained in your textbook, which is why I wanted to make sure I included this one in your video. So by CPCTC, this means corresponding parts of congruent triangles are congruent. So whenever we use CPCTC, we should have before that some statement that says two triangles are congruent, and then we can use CPCTC to say that any of the corresponding parts are congruent. So I can say that angle ABC is congruent to angle ACB, again by CPCTC. Let's take a look at another proof. Here we're going to prove the Angle Sum Theorem, and that says that the sum of the measures of the interior angles of a triangle is equal to 180 degrees. So you are welcome to work ahead and see how you do, or you're welcome to work through this with me. Here, for my given, instead of saying for every triangle, I'm going to be specific and name a triangle. So let triangle ABC be a triangle. What am I trying to prove? That the sum of the measures of that triangle, so I'm going to go ahead and draw the triangle because it helps to have something to look at, that the sum of the measures of that triangle are equal to 180 degrees. Two ways to write that. I can say that the measure of angle ABC plus the measure of angle BCA plus the measure of angle CAB is equal to 180. And again, when we're naming angles, remember that that middle value tells us the vertex. So ABC would be this angle right here. BCA would be this angle right here, and so forth. The other way to write that is alpha triangle ABC is equal to 180 degrees. Those mean the exact same thing. All right, so now moving forward with our proof. This one in particular gives us a hint, and the hint says let ABC be a triangle. Well, we already did that. Draw a line through C that is parallel to the line through A and B. So essentially they're saying this is a nice line that you have, and we want a line parallel to that. And then apply the converse to the alternate interior angles theorem. So you might be saying, is that legal? Can we do that? Well, the answer is yes, if. Yes, if you say it in your proof, it's legal. So we're going to say construct a point D. And where is that point D going to be? Outside of the triangle. So on the exterior of triangle ABC. Now, any point D? No, we want point D to basically construct this line that goes through C. So on the exterior of ABC, such that angle ABC is congruent to angle BCD. So let's think about what I'm doing here, because sometimes it kind of feels like I'm just making stuff up out of nowhere, but here's why. I want angle ABC to be congruent to angle BCD. Well, why am I doing that? Because I want to basically show that these two lines are parallel. And I can show that the lines are parallel. Again, I'm going to put D over here. I can show that the lines are parallel if alternate interior angles are congruent, right? That's something that we know about parallel lines and angles. So such that angle ABC is congruent to angle BCD. Now, I don't need a reason for that one because I'm constructing. But now I'm going to say hence, and a lot of times mathematicians use hence instead of therefore because they save therefore for the end. But basically I'm saying hence, the line AB is parallel to the line CD. And that's what I wanted. I want these things to be parallel because I know a lot of stuff about parallel lines and angles. All right, let's continue. Remember that my goal is to talk about the angles in the triangle. So knowing now that I have a pair of parallel sides, I should now be able to also say that angle BAC is congruent to angle, oops, I can't name that angle. So now I need to have another point. So that's what we're going to do next, just so I can name the angle. So, hence AB is parallel to CD, and that was by the alternate interior angles theorem. Always give a reason. So now I'm going to say construct E on that line CD such that, and now this next part is going to show where on CD point E is. I need C to be between E and D. Okay, so again, why do I have to be so specific in my proof? Because you have to assume that the person reading your proof is not looking at your diagram. Anything you put in the diagram, you need to be very specific about in your proof. So I'm constructing point E such that ECD is basically the order of the points on the line. Now, again, that was a construct, so I don't have to give a reason for that. But now that E is there, I can say hence, and now that the point is there, I can say angle BAC is congruent to angle ACE. Again, why can I say that? Because I have two parallel lines, and those are alternate interior angles. That is actually the converse to the alternate interior angles theorem. When you already have the parallels and you're saying that the angles are congruent, that's the converse. Now from here, I need to bridge the gap between, I've got these angles and I need them to add up to 180 degrees. So what else do we know about 180 degrees? Well, we know that's the measure of the angles that make up a line. A line is 180 degrees. So how can I do this now? What I'm going to look at is the linear pair theorem. The linear pair theorem says that if you have two angles that make up a line, those angles add up to 180 degrees. Now I need to do it twice because what do I have? I have three different angles. So I'm going to use red here to show this last angle. And technically, I would have a different number of lines to indicate which angles are congruent to which angles. But looking at this picture, because I've color-coded it, it's clear where I'm going with this. I can say that the measure of angle ECA, so that's that purple angle right here, ECA, plus the measure of the red angle. Let's just use our colors so we're very clear. The measure of angle ECA plus the measure of angle ACB plus the measure of angle BCD is equal to 180 degrees. And I'm going to say by two applications of the linear pair theorem. And the linear pair theorem, of course, says if you have two lines that make, or two angles that make up a straight line, they equal 180 degrees. So I've just done it twice. And then I can say by substitution, and then I'm just going to replace the purple angles. So instead of ECA, I've got the measure, well, let's put it down here. The measure, instead of ECA, I'm going to use BAC plus the measure of angle ACB. I didn't have to replace that one. Plus, instead of BCD, which is down here, I'm using the other green angle, so the measure of angle ABC is equal to 180. Well, that's what I wanted up here. ABC, BCA, CAB is 180. So my final step, therefore, and then I'm going to use the shortened version because I'm obviously running out of room. The sum of the measures of triangle ABC is equal to 180. And then the little tombstone that says that proof is complete.